I'm gonna click on the here. We get access to the Department of the Treasury in the US, and we have data, okay? I will say interest rates, and we have daily treasury per year. Per year curve. This is what we're gonna do. We get data, we get dates, and we have like a different maturities ranging from 1 month up to 30 years. This is the horizons in which the US Treasury is easy. If you want to borrow, if you want to lend to the US government, that's the maturities, that's the bonds. Below 1 year, those are treasury notes. Above 1 year, and including one, above 1 year, that's bonds. Okay? So those are the maturities. So I'm gonna come here, I'm gonna take this label. So where is the and the PDF file, the workshop form, you see the graphic with the picture, right? Click on it, there's a file and it takes you to the website. Okay, so we select that range because it's the maturities. That's going to be N for us. Okay, I go to the Excel file.
You want to data, right?
Huh? Let me go over that again. You go to data. Okay, data, and then interest rates, and we have the daily treasuries. Okay, and that first option, that's where we are given the data from the curve. Very limited curve because we have just those maturities, but that's what we have. So I'm gonna take the first label row. I'm gonna copy in my Excel file, something like that. Okay. Date. We have January the 2nd, January the 3rd. Don't get confused by the American notation. Month, date, year. And that's at the very beginning, right? Yeah. You see all this data. You see that, for instance, the 1.5 month maturity has been issued first time ever in 2025. Before, we didn't have that maturity. From time on, in January or something like that, right? Mid-February, this guy is being issued. Okay. So I think that tells you that there is a lot of action concentrating the short-term months. People like when there are so much interest at the maturity, now the US Treasury is issued. And we are going to go to the more recent date, which is October 27th. Right? That's the dates. Those are the maturities. Take this thing. Copy, Control C. Then I go to the Excel file. Control V. And copy paste those files. Now I have a problem because in my Spanish system that dot is not understood. So Excel is regarding all these observations as string character, as if I had written something. I want that to be a proper number. So what I'm going to do is just change that point by the comma. So I'm going to underline these things. I'm going to go to, this is where the fine here, empty. Let me see what is the version here. Okay, here I have this find and replace. So I'm gonna replace. I want to replace the dot with the comma, and I will replace all. Okay. So we check that this is the.
This one?
Yeah, it's the code.
This one?
So right now it's working for me. If you have the idea point, because you have the dot, right? I went to the find and replace. find and replace, and it was that as simple as that. So find and replace, we went to replace,
Sorry.
and I say look for the dot,
Okay, great.
replace it with the comma. And then
Great. Thank
this
you.
is understood as, right, if for instance I
Great.
take this number
So
and I
how-
multiply it by
so
2,
it's like
that's
the date.
not
Date.
you know, the 80.
Yeah.
Before, it was just treated as a character, so not very useful for what we want to do. Okay? Now,
Thank you.
I'm going to arrange data in a more convenient way. I put it this way, which is the table format. We have the original in the data, but I would like to have this data in a column format, because we are going to sort of work from like that. So I'm going to take this thing, I underline, right button, copy. I'm going to put, for instance, the photos here, right button, paste special. And I'm going to say transpose. And by doing that, we have this format, which is much more convenient because it will allow me to do things over here, right? Okay, guys, understood?
Can you do it again?
Yeah. So I select the data, right button, copy, and then I went over here, let's pick one, then we will arrange later. And then I say paste special, and then transpose. So this thing will be rotated, and the rows become columns. And that's perfect because now we can work by columns, which is more natural. We have a short number of rows, so it's much more convenient. So that's what we are going to use. I'm going to remove these things, we don't need it anymore, so delete. Okay, I'm going to sort of remove this as well, right? We are here. Date, I'm going to put it right here. That's going to be, format that will be 27 October 25, right? And this is Gilles to Matthew. I'm going to give format like this, just to make it look nicer. Excel is cool for that. So guys, don't be shy or lazy. The visual thing is important in Excel. It's one of the advantages. We do that. And I'm going to start saving. That's another very important thing, guys, that particularly in the exams, making constant thing as we progress, as we go, okay? So save as. Put it right here. This is workshop 4. Okay, so this is our year to maturity, and the most natural thing to do is to make a plot, right? So I take these 2 columns, we go for insert, recommended chart, and then I'm giving this kind of limited options. None of which is good for me. I want a line graph. The problem with this bar line is this character, right? 1 month, 1.5. That's ugly. We need to remove this. 1 month. And then 1 year. Now we need to standardize. That's intuitive information, but untractable from a practical way. We are going to express everything either in months or in years. What do you prefer? What sounds more natural?
In months.
Months or in years?
I mean, it's more natural in years.
So we are going to express everything in years, right? We have this thing already in year. So 1 month. 1 month is 1/12 years. So all that. Super accurate, of course. 0.08 years. The units of this thing is now years. 1.5 over 12 years, 2 months, 2 over 12 years, 3 months, years, 4 months, okay, 6 months, CC as 0.5, and then we already have years, but I want this numerical express, right? So 1, 2, 3, 5, 7, 10, 20, 30. And you may ask, what is the 15 years horizon? The answer is there is no, because they don't issue at a 15 years horizon. They just reporting what they have. All right. If I underline these things, insert, recommended graph, and now we have now something that is much nicer, right? Okay. We have the maturities over there. We have this thing. We may zoom it, right? We are looking something between 0 and 5, so we may kind of get closer. If you want to do that, click on this. The Excel object is one of the more complicated things in Excel. It has a lot of things. It has those lines, it has these lines. Of course, it has the main line. It has the chart title. I call it G core, right? That's going to be G, US, G to maturity. But I would like to have this axis, not between 0 and 5. I would like to zoom it, and let's say between 2 and 5, right? So click on it. We are giving options. Okay, right button, format axis, and we say minimum 0, maximum 5. Alright, so minimum, let's leave minimum 2%. So this graph is going to be more informative. Now we are kind of zooming. We may zoom even 2.5, right? Even 3. Okay, and we see that we have this kind of curve that is increasing, etc. Okay, all of us? Huh? Yeah. Click, right button, and then format axis. We sort of give it what we want. We put it from, it was between 0 and 5, now I sort of zoom it, and now it's 2.5 to 5. And the same thing if you like for this one, okay? For this x-axis, we can do the same thing. Right button, format axis. We don't have anything beyond 30, so we may say something maximum is 30 years, right? And now we are zooming in this particular way. If you like, yeah, fine. Now, there is something wrong with this graph. Something very misleading in this graph. What?
That it's important in the first 5 years.
No, that's what the data showed. That's not wrong with the graph. That we may sort of say that's what the market says. Apparently, if you borrow right from this horizon, it's making this shape. But something is very misleading in this graph. What? You are being tricked, and you don't even notice. And that happens very often to people that are not used to the analytical, the analysis. You are being tricked right now by Excel. How? Isaac.
The graph seems smooth, while in reality the scale is too small.
It seems smooth. You think it's smooth?
It's not smooth.
It's not smooth.
The scale is.
It's big. Isaac is noting, for instance, this kind of kinky behavior, right? Click, click, click. But there is something even more serious than that. That's a problem. But something even more severe is being going on. What? Look at 20. Look at this area. Look at this area, right? Do we have values for yield to maturity between 20 and 30 years? Do we? No. We have 20. And then we jump up to 30. But Excel has not done that.
No.
You see? You didn't notice before. You've been tricked by Excel. It's making believe that we have a kind of data around here that makes this thing. But that's not reality. That's not necessarily true. We simply don't know. What we know, what we have is the dots. The dots, which is marked with the Excel with dots, that's the real observation. Everything else is an interpolation. That's why the graph looks so kinky, having those kind of corners, because Excel is taking the points and just drawing like a child. It's just connecting two consecutive points with a line. This is linear interpolation, and it gives us this impression. I would say something like, all right, let's say that I'm interested in the 25th horizon maturity. I need the yield for that. I will say, okay, it's something around 4.5, right? Is it? No, it's just how Excel has filled the empty points for you. And that has two sort of weak points. First of all, Excel did it linearly, connected the 2 points. And because this is just connecting 2 consecutive points, it's making this graph looking sort of rough, having these kind of vertices, right? Well, first of all, if you want to interpolate things, I will prefer something that takes into consideration all the set information available. This is not what Excel did. Excel, in order to fit the empty area between the 20th yield to maturity and the 30th, what it did was just taking those 2 points and constructing the line. And when you did the same analysis between 10 and 20, just look at the 10 and 20 values. I would prefer having the whole set of information and fitting some function that sort of takes into consideration everything that we have, all the data, not just this kind of local information, but the whole set of information at once. So this is not what Excel did. I would like to do some fitting, but not local fitting, overall fitting. And then comes this type of smoothness, because Excel has chosen arbitrarily linear fitting, interlinear interpolation, is making this kind of rough, not discontinuity, but making this thing, not smooth. We didn't see that in the curve fitted by the European Union, which, by the way, is precision measurement is here. We see something very smooth, right? I would like to have this kind of smooth fitting, avoiding this type of rough behavior. This is polynomial fitting somehow, or kernel fitting somehow, or is curve fitting. This is what we want to engage. We are going to use some form of interpolation, but superior. And you will see what is the payoff of all the analysis we are going to do. All right. So, I want to do the Nelson-Siegel model. I want to fit according to the Nelson-Siegel model. The Nelson-Siegel model has this equation. Let me take it over here.
Have you seen the film structure of which it is? No.
This is it.
This is it. It's just, me surgió la duda ahora que han pasado las slides.
That's the theory structure. That's the theory structure of the US. Only that it is kind of partial thing, right? We only have these particular maturities. And my point is, in mind that you need something like, let's say, 5.6 years. What is the yield to maturity to 5.6 years? And you don't know what it is. And you will tell me, well, but I have here something like a 5, then I have something somehow interpolating 5 and 7 should be giving me something between 3.6 and 3.7, right? That's what we are doing, but in a sophisticated, elegant way. So I'm gonna take this over there, right? This is what we want to think. That looks very ugly. This expression tells me what you observe. We can reconstruct it by taking advantage of, first of all, n. N is date. So n would be 008, 0.25, or 5. Then we have 1, 2, 3, 4 parameters that will control the shape of the underlying curve. Beta 0, beta 1, and beta 2, which are not very different in spirit of a linear regression model. We have my yield to maturity is driven by a kind of constant effect, beta 1. Then we have a beta 0, sorry, a beta 1, which is multiplying a kind of regressor, if you like, right? That parenthesis, I'm going to call it x1. And then we have another beta 2, which is multiplying another parenthesis, so let's call it x2 in order to bring in something that looks familiar. And this is what we are going to try to do. That's this structure of my prediction. And
That's our case.
that's our case.
So the lambdas, you don't.
Lambda is the guy that spoils everything here. Is the guy that is gonna give us a headache. If lambda wasn't there, we could fill this model with our OLS. Because everything is linear in parameters. But that lambda that appears like ugly things kills us. And then, of course, you will say, but Antonio, you have this perfectly, this what it doesn't is, the reality is what your model says, so you have like a 100% accuracy. Now, we need to introduce the error there to conciliate this idea. No, I'm going to make errors. Errors are going to be the distance between the real observation to what my model says. So I need to construct the relation. That x1 is the first parenthesis, right? So let me take the formulas. I'm going to put it here so we all see it. I'm going to make this screenshot and bring it here. And then I will accommodate this, don't worry. Okay? So I can create this regressor because it's a function that depends on maturity, and I know the maturities. I have it, it's called A. And then if I knew lambda, that lambda guy, that bloody thing, if I knew lambda, and n, I could construct x1. And then that x2 is x1, right? This expression here is this expression here. So this is x1. And then we need to take this minus lambda thing. Okay, that's not, it looks complicated, but it's not so much. Where I'm gonna go here, for instance, in column H, then if I need more space, we can move things. I'm gonna say, all right, you need that lambda parameter, right? Let's guess something. Miss it. I don't know, we need it. Yes?
Es 0.05.
0.05. Okay, that's Nice's guess. But because we have this guess, now we can construct x1. I can go here and say, okay, x1 is a regressor that depends on n, which is something that we don't need to guess. So I'm going to sort of separate it because I'm kind of a econometrician, and this is something that for us is kind of mandatory. So, all right, and then we have this parameter, which is an argument that we need to guess. But then, everything is not very difficult. All right, so I have that x1, and the formula tells me how x1 is. All right, I need to open a parenthesis because we have to construct a ratio of 1 minus the exponential of minus lambda. So that was the value that we are guessing, right? And if it is a good guess, we are super nice, and if it's a poor guess, we will have a lot of things to do, but we are moving in the right direction. We are stepping, right? First step of a long way. Now, we are going to call this guy several times. So I press F4 to lock it. and I close the exponential and the first parenthesis. And then we need to divide this thing by lambda times the maturity. Sorry, I'm missing the maturity, right? We have minus lambda times the maturity, which is what we have here, column A2. That's fine. I will copy paste that, so that A2 can be a free cell, the parameter or not. Then I close the first parenthesis with exponential, I close the second one, and we are good. Now we need to divide that thing by, and the formula tell me lambda n. Okay, lambda is what we have here. I press the F4 to give it, to lock in, times the maturity. Alright? Take your time, guys. Bypass that here. So now, x1 is our parameter, is that we are regressor, right? And right now you're going to take a number. Good or not, that's what I don't know. But it's taking numbers. So this expression is moving from the pure theoretical thing to something that is taking shape. Okay, I hit enter, can I? Okay, I'm just writing this expression. I go, okay? Done number. Alright, whatever. Fine. Now, I copy paste down. We copy paste down, and we have all those values. S1 is no longer a problem. Next, we have this other parenthesis here. So I'm going to call it S2. This guy, this function, depends only on the maturity, but we know it. And again, of this lambda parameter that we don't know, but we are guessing. So if I know n and I know lambda, then I can compute numerically what x2 is. So let's go for it. What is that S2? Is this expression here, but that expression we computed before, that's x1. This beginning is the same as what we have called x1. So I can make a reference to what we have to the right, sorry, to the left. Whatever you did there, I'm gonna build on that thing, C2, okay. And then what? Then we need to subtract the exponential of minus lambda. So I make the reference to where lambda is, I lock it, times maturity. And maturity is here. So that was easier. And then I have C2. Okay? Somebody have problems. Somebody or Matilda. One of this. Matilda, you're not in somebody, right?
Finley.
Simply. Problems?
No.
Everything good?
And you go to UX1.
What? This one?
Yeah.
You got it, Ignacio? Okay. Numbers should be the same one. We are working, if we are working with exactly the same numbers, we all should have, we are really, no, there's no randomness, we should have exactly the same numbers. Are you getting the same, did you copy the same yield to maturities? So you have 409 here, and this 008, and it's a number. It's a number. So when you do this thing,
No, I have the first, like, only 1 year, I have it good, but after the year, it says value and everything, so, I don't know.
check what happened there, because it's not working clearly for you. So before going further, let's make sure that no, that's not the maturity. You see that, that's not the core that I have.
225 and
Yeah.
Luego, tienes tu punto la de la que dependo.
Sí, es que me ha sacado primero.
Porque nos copia los lugares. Es 4,09 son 4,57. Vale, o sea, que puede ser 4,09. ¿Cómo es posible que tiene que llamar 4,09, 4,09 por cerrarle con 4, es 89, es 87?
Ah, no, sí, vale, sí, pero que
Dibuja los
dice
lugares. Se me quedan los lugares.
o sea, los de la meta no se ve.
Ese, y ahora déjame entender primero qué está pasando. Porque que no se puede ser capaz de dibujar la misma. Algo pasa, es lo que le digo.
I guess.
Ah, que me da con el
Bueno, poco a poco. Lo mismo, tienes que quitar los años que pongas de ese no, el dibujo de tu figura no es la mía. O sea, no has dibujado, se le está dibujando otra cosa. Dibújalo otra vez. Eso que está yendo a la derecha es como si no tuvieras caracteres. O sea, es como si tuvieses letras. No, coge solo los números. Coge solo eso. Y ahora dibújalo. Insert, figure, con insertar. Gráfico recomendado. Vale, eso sí. Eso sí. Ya empezamos a trabajar desde ahí. Okay guys, before moving on, more problems. We need to sort of make sure that we are on the same page on class. Not the, we are gonna, the snowball is gonna be farther, bigger very soon. Okay? So, this is a formula for the second factor, and now I copy paste down. We are not interested in these values. This is auxiliary elements that we need to compute the prediction. And now the prediction is what? The predicted value is this thing. So let me emphasize this idea. Okay? The predicted value takes beta 0, beta 1, beta 2, and then it's taking those x values. So I'm going to create a new column, and that is the yield to maturity from Nelson Siegel. Because you are using, your prediction is not just a simple guess, it's a regular guess. It's a guess constructed according to this model. Alright? So we now need another 3 parameters that we need to guess. Beta 0, beta 1, beta 2. We need the x values, right? And the s values, we have it. So if we give values to beta 0, beta 1, beta 2, we are able to construct a Nelson-Siegel estimation given our values. So beta 0, let me do this thing. Roberto, has a question?
No.
So this is the mean. That would be a very good guess, right? I'm going to start with the mean of the yield to maturities. Let's stay over there. Sorry, it's not mean, it's average. No, it's average. Okay, let's start here, right? 3.9. That's going to be my beta 0. And for beta 1 and beta 2, I'm guessing 0. I know what you say, but I'm 0. I know what you say, but let me start from here. Now, given beta 0, beta 1, and beta 2, and given the x1 and x2, now we can construct the prediction of the model. And the model tells me, take your beta 0, there we go, log, plus, take your beta 1, this guy here, log it. And you multiply this thing that you have called x1, which I have it right here. That one, free, because we want to copy paste down, and these cells need to be allowed to move. And then you will take this thing that you call beta 2, so this guy, lot, times this other variable that you have created, and you call it x2 in column D. That's the recipe for the zero to maturity according to the Nelson-Siegel model, given the parameters that you are choosing. Take time, guys, and when you are done, we move. We are very close to the end. It looks complicated, but it's much more simple, and we are taking insight of how an econometric model, when you do estimation with the least square analysis, this is what is happening inside of the algorithm. So 3.90, and then of course it's very naive, right? We will have 3.90 all the way around, all the way low, because beta 0, the other parameters were 0. So let's say beta 1, I say 0.1. Now that's slightly changing, right? And let's give it the other value, I don't know, 0.2. Just to see how things go. Alright? Now you have different values. Fine. This must be terrible. Or this is very bad. This is very bad because good, of course, what is good and what is bad? Good is whatever my model says, predicts something that is close to reality. And it's bad whatever my model says something which is not very precise. So we can construct the error of the model. The error of the model is the distance between the real value and the predicted value. You made all this error. And of course, we may say, that's the error. The real value minus the predicted value. But why not the other way around? The error could be also defined as prediction minus real observation. And you're fine. In reality, it's true. I don't care about the sign of the error. We just care about the magnitude. So that's the distance. So we are going to put the distance squared. Error squared.
You're subtracting the 4, the E2 minus B2, right?
V2 minus E2. The real observation is 409. My model says 4. I'm making an 009 error. So you see how the model is constructed. Right now, when I put the error, I have this structure constructed. The real observation is whatever your model says plus the error. If your model is good, errors are going to be small. If your model is bad, errors are going to be terrible. That gives us the identification principle. The errors depend on my choice of the parameters. So if I change the value of the parameters, the errors change. So I can identify the best parameter, the best combination of parameters by picking up the combination that minimizes errors. Well, not errors, errors squared. So we go for error, we take the error, and we square that guy. This is a mathematical trick. This is a way to get rid of the sign. And it's just one possible way to get rid of the sign. But mathematically, when it comes to computation and optimization, is the best way possible. We may opt for something different, like we're not taking the absolute value, right? This is much more intuitive, but computationally, it's much more difficult to work with. That's why we take squares. The square is a more tractable function than the absolute value. If you think of the squares, we have something like this. If you think of the absolute value of the epsilon, we have something which is very similar, but it has the behavior that mathematically is kinky behavior, right? This thing, mathematically, is very complicated to work with. this function square is smooth as a derivatives. That one is much more tractable theoretically and computationally. So we prefer this thing over that thing, even though they are doing in essence the same job. You are removing the sign, you are having a convex function that can be minimized, but the squares is much more tractable. Alright guys, so we are the end. This is my error square, okay? So I'm gonna make a little, we need some room here. Insert, not so much. Okay, couple of spaces. And now I'm gonna take those formulas. I don't need them anymore. I need the space, okay? And saving all of that. Okay, so first thing, in this graph, so far the blue line shows me the real value, so to speak. I want to put here also my model. In Excel, this can be done like this. I'm going to do it twice, okay? Just I first show you the path, and then I repeat. I'm going to select the graph because I want to activate this object in the workbook, right button, and then I'm going to go for select data. Select data, right now we see what we have. We have that series with those values. Then we are going to go for add. I will have to add a variable that has a series name. The series name is going to be yield to maturity. That value has, that series has X values. X values is maturities, so these values here. And the Y values is my yield to maturity predicted. So I'm going to be okay with that, okay. And then we will have in the graph the series, the process that was observed naturally, right, what we have, and the orange lines shows me the fitting that we are guessing. And we see that it's terrible. Listen, shame on you. We are going to improve this, I promise, very quickly. Okay, no, not a problem. And this is one of cases, we need to start. And every algorithm does this job. When you do optimization, this is called the initial condition. And you need to start somewhere. The initial condition is, unfortunately, very important. If you start from a good initial condition, things are going to be fast and accurate. If you start from a very bad initial condition, the optimization routine is going to be very bad. Well, yeah, but we need to start at a certain point.
Lambda doesn't have to be between 0 and 1, right?
Lambda needs to be what?
There's no constraint for the value of lambda.
No. Can be negative. Yeah. Actually, it's going to be negative. Okay, guys? Let me repeat how we inserted the graph. Okay, that's important. Graphically, make it look nicer. And objects, the graphical objects is important to handle. So, we select the graph. Right button. We look for select data. In select data, we are given different options. You can manipulate, you can change the x's, the y's, but that's not what we want to do. We want to add. So we look for the add. I know it's very simple, very straightforward. A field for series name. The name is going to be this yield to maturity next on series. A series for whatever is your x-axis. My x-axis is A2 to A15. The values taken by x. And the y values is the values that we want to plot here, which is the yield to maturity next on series. Okay, we are good. Okay? If I click here, see that if you see, if we select it up here, it says add chart things. We can give it the legend. So we would like to have something like this, or maybe like this is fine, okay?
The X is the yield to maturity, right?
What?
The X is selected.
X is maturity. The y-axis is yield to maturity. Okay, this is the data as it came, and we plot it with Excel, and this is right now what our model says, given the parameters. And because we are guessing, we should not expect to see anything, brilliant. Yeah, that's not the point. Now, we need to work with that right now. So, what we're gonna create, this is the parameters. Now, down here, for instance, I'm gonna create the loss function. The loss function, econometrically, is the most important object. This is the function that you use as a criterion to identify the parameters. What is your loss function? The loss function for us is the sum of the square errors. So this is like a score. The loss function right now is 1.64, and this is informative on how good and bad the parameters are. Look what I'm saying. If I take beta 1, O1, this value is 1.64, right? Now in my lab, rather than beta 1.1, I say beta 1 is 2. What happens is that the loss function goes to 49.65. That value is better or worse? We have two cases. Which one is better? The one that reduces the errors. I have this alternative fitting, and I can check numerically how good and how bad we are doing things by looking at the loss function. So if you give me two sets of different values, I can use the loss function to discriminate which one is better. And now, which one will be optimal? The one that makes this sum of the square errors the smallest possible. And we would like to start guessing, and we have 4 parameters, multiple combinations. That's gonna take long and it's gonna be hard. Unless we use some algorithm that is intended to do this job. So this is what the numerical optimization is about. You set the model. You start from certain point. And that algorithm is going to start to look for the minimum. So let's say that we have a function that looks like this. This is my loss function. I want to minimize that value. And that value that minimizes the optimal value is here. So this program asks for the give me something to cost the loss function. We already had it. That's the loss function, right? And now we have certain initial point. We are, I don't know, over here. That's not the minimum possible. Now, the algorithms of numerical optimization will compute derivatives numerically. They are going to start checking this function, making small steps, saying at this point you have a negative derivative, you can go down. And those algorithms will take steps and move up to here. And then they will keep on. And if I go up, what happens? The derivative is possible. So this algorithm will identify a point in which the derivative is not negative, meaning you have room to go down, and it's not positive, meaning you are passing by the minimum already, looking for some point in which the derivative is 0, because that's the condition of option. That's what this algorithm is going to do for us. We will not be guessing more.
So we're gonna minimize the error term, right?
The sum of the squares, this loss function,
We're gonna get the beta that minimize the error, the loss function,
and the lambda.
and the lambda.
The 4 parameters, we are going to make a cell to look for the combination of the 4 parameters that minimizes these distances. And to do that, we need special algorithms. So it's high tech. It's not something that, we may do regularly. But fortunately for us, we have the solver. We go for solver. The solver gives us these options. All right, first of all, you want to do something with a function. First question, where is that function? So here we let the cell know where is my objective function. It is at K6 in my case. Go for K6. Okay, what do you want to do with K6? You want to maximize, you want to minimize, or you want to set that value equal to something? What do we want to do? Minimize it. You will never get 0. That will be an equation. This is not an equation, forget it. There will be such a thing as perfect fitting. We want to second best We want to minimize that thing. Is it what you guys are doing with is squares with Alberico? That's exactly what you are doing, or is that you take advantage of the fact that you know the formula. Here we need to do this numerically. So if you program with Python more competitive things, that's what you will end up. The algorithm, the only thing that is everything's a little bit more primitive, more manual, but we are doing it anyway. Now, by changing variable sets, you want to change the values of certain sets in order to move the loss function. Where are my sets that I want to change? Lambda, beta 0, beta 1, beta 2.
But beta 0 you put the name because arbitrary or?
Yes.
Okay.
First, it was my first guess. Then we are moving. Natalia, are we good?
Yes.
Sure?
Yes, yes.
You are lost.
No,